The transition to electromobility rewrites the strict boundary conditions of vehicle dynamics. What you see here is the physical limit of rubber, warping under the strain of an electric drivetrain. Electric vehicles introduce three distinct physical challenges. First, battery packs create massive downward weight. Second, electric motors deliver peak torque, the rotational force sent to the wheels, instantly at 0 RPM. Third, the absence of an internal combustion engine removes background noise that traditionally masks mechanical friction. If you mount a legacy tire designed for a gasoline engine onto a modern electric vehicle, these forces collide. The traditional tire architecture is not built for these specific mechanical loads. Standard tires buckle under the added pressure. This compromises steering precision, reduces battery range by up to 12%, and causes rapid, uneven tread degradation. To maintain performance, engineers are now rebuilding the automotive tire from first principles. Consider the weight constraint. An EV battery pack often pushes vehicle mass over 2.5 tons. This alters the vertical load on the contact patch, the specific area of the tire tucking the road, requiring a stronger internal structure to prevent collapse. Next, consider the impact of the torque. Because an electric motor hits maximum twisting force immediately, starting from a stop creates a violent shear force that tears standard rubber compounds apart. Finally, the acoustic constraint becomes a priority. Without an engine to cover the sound, the friction of tires rolling across the asphalt becomes the most disruptive frequency inside the cabin. These factors make legacy tires physically incompatible with EV physics. Solving this requires an overhaul of the tire's structural architecture and chemical makeup. We must address the mass first. When a heavy vehicle corners, centrifugal force pushes thousands of pounds onto the outside tires, bulging the sidewalls outward. The engineering solution is to reinforce the sidewall to increase the load index. The load index is a numerical code indicating the maximum weight a tire can safely carry. These reinforced casings are marked as XL or XL+, to prevent buckling under high mass. This heavier mass actually helps reduce hydroplaning risk, where water builds up between the tire and the road. Because the weight punches through standing water, engineers can narrow the drainage channels, leaving more rubber in contact with the ground for improved dry grip. However, the structure must also solve the noise. At city speeds between 30 and 50 kilometers per hour, the humming resonance of the tire against the road becomes highly obtrusive. Manufacturers address this by bonding a specialized layer of acoustic polyurethane foam directly to the inner liner of the tire casing. The air cavity inside a tire acts like a drum, amplifying road noise. This foam layer is tuned to absorb those rolling vibrations before they can travel through the suspension and into the steering column. Field data indicates this structural addition can reduce interior cabin noise by up to 9 decibels. While structural reinforcements manage weight and noise, the primary metric of EV success, battery range, requires a material overhaul of the rubber compound. Rolling resistance is the energy lost as a tire deforms while moving. Minimizing this is the most effective way to extend an electric vehicle's range. The impact is measurable. Shifting a vehicle from an EU C-label tire to an A-label can reclaim up to 50 kilometers of range on a single charge. This chart shows the material distribution inside a modern tire. We are focusing on the filler and synthetic rubber portions, which make up over half of the tire's weight. Traditional tires rely on carbon black as a primary filler to maximize tear strength and wear resistance, but it cannot maximize wear while simultaneously lowering rolling resistance. Improving one compromises the other. This chart displays how the tread compound governs performance. Look at the blue bars. The chemical compound dictates nearly 60% of the tire's wet braking and rolling resistance performance. To optimize range, engineers replace carbon black with high concentrations of silica. Silica reduces the energy lost to heat during deformation, lowering rolling resistance without sacrificing wet grip. This chemical overhaul maximizes efficiency and safety, but it introduces a secondary, invisible problem: electrical isolation. The material shift has a physical consequence. Silica is an exceptional electrical insulator. It does not allow current to pass through it. This creates a hazard. An EV running on high silica tires risks becoming isolated from the road, preventing the car from safely discharging static or system energy into the ground. Engineers use a specific internal architecture to bypass this insulation. Look at the three main components of the tread: the cap, the base, and the wings. The cap is the outer high silica layer. It provides grip and range, but acts as an electrical roadblock. Beneath it lies the highly conductive tread base. The workaround is a physical bridge. Engineers extend a narrow section of the conductive base so it cuts up through the insulating cap until it makes direct contact with the asphalt. This extended base creates a conductive bridge. It allows electrical energy to flow from the vehicle through the casing and safely discharge into the road surface. This structural fix is invisible to the driver, but it is a mandatory safety mechanism for modern electromobility. The conductivity paradox demonstrates the extreme compromises required to optimize EV range. It leads to a final, unavoidable trade-off: the lifespan of the rubber. These highly engineered EV tires are now colliding with the real-world expectations of consumers. This study from J.D. Power tracks original equipment tire satisfaction in the luxury car segment. The data reveals a widening satisfaction gap. EV owners frequently report frustration because they expect their tires to last as long as the ones on traditional gasoline cars. This trend persists across the standard passenger car segment as well. As EV adoption grows, so does the realization that these tires wear out significantly faster. The physical limits are clear. Combining high vehicle mass with instant torque creates a shear force that rapidly strips away even the most advanced silica rubber. For heavy EVs weighing over 3 tons, the wear is intense. Some owners report complete tread degradation in as little as 6,000 miles. This wear rate is not a defect. It is the mathematical cost of supporting extreme weight while delivering instant acceleration. Driver behavior is the only variable that can mitigate this. Learning to temper acceleration reduces the shear stress on the contact patch, prolonging the tire's life. The modern EV tire exists as a meticulously tuned node in the powertrain, built through intense physical compromises. Optimizing for range and cabin silence means accepting the hard reality of rapid rubber degradation.